Today, we're going to take a look at section 4.5, which is the one additional piece of information that we're going to take a look at for finding antiderivatives. For those of you who do go on to chapter 5, which is in Calc 2, all of chapter 5 is additional integration methods. That's what it is. So this is the one additional piece of information on solving antiderivatives or finding antiderivatives that we have in chapter 4. So to start with, we're going to consider the function y equals sine of x cubed minus 4x. Okay, it's a function you've seen before or things like it. And I would like for you to take a moment and to write down what you believe the derivative, not antiderivative, but the derivative is. So what is the derivative of sine of x cubed minus 4x? What overarching rule are you using as you're doing this one? The inside-outside rule. It's called the chain rule. Exactly. So this is a chain rule problem. So the sine is what's on the outside. So what's the derivative of sine? Cosine. And we rewrite the inside as is. And then we do the derivative of the inside. And what's the derivative of the inside on this one?
X squared minus 4.
Close. It's at 3x cubed. I'm sorry, 3x squared minus 4. Yeah, so you just had the 3 off there. Yep. Okay, so we have that derivative of the outside, the derivative of the inside. So what we're going to do is we're going to be working with functions that start out looking like the part that I just wrote down. It looks like a product. And going backwards into something that was actually a chain rule if you were taking the derivative of it to begin with. So one option when we are looking at functions that look like products is something called substitution or integration by substitution. So when it looks like the inside of a function is the other component of a product, that is the case when substitution or integration by substitution is a valuable tool. So if you consider the y prime above, x cubed minus 4x would be considered an inside function, right? It's inside of the sine or the cosine, depending on which of the two versions of it we're looking at. If we're looking at y prime, it's inside of cosine. And then its derivative, 3x squared minus 4, is actually the other piece that's being multiplied. So what we can actually do is that we can let u, that's terrible, u equal x cubed minus 4x. And then when we take the derivative of u with respect to x. I know this is not notation we've used very frequently, but it was a notation we saw, df dx or dy dx, those kinds of notations. What's the derivative of the x cubed minus 4x? The 3x squared minus 4, the outside piece that we found when we were writing those pieces down. And if we just adjust this a little bit, take a look at what happens. And we can actually see that du is equal to the 3x squared minus 4 times dx. Okay, so it kind of looks and feels like I just multiplied dx to the other side. Do you get that sense? All right, so take a look at what happens when we actually put all of this together. Let me set this down so I get it rewritten correctly. If we take the antiderivative of the cosine of x to the third minus 4x, 3x squared plus, was it plus minus, minus 4 dx, okay? So over here, we're taking this piece, everything that was written right here, all right? And we're going to take the antiderivative of it. And of course, what we're anticipating is that we should end up back here. I mean, that's where it came from, right? We're supposed to be able to get back to where we came from. That's what antiderivatives are. So if we take this piece right here and we do a little bit of substituting, in particular, we've just said that this piece is going to be called u. And we've said that everything right here at the end is going to be called du. Right, that's the substitution step that we made. We relabeled things. We renamed them. The other pieces are still there. I still have the antiderivative at the beginning. I still have the cosine. None of that changed. None of that was substitution pieces. So think about what we have now right here. It's just cosine of u. right? A simple antiderivative. We can take that, no problem. What is the antiderivative of the cosine of u? Yeah, it's sine. It's sine of u. Potentially plus c, right? We might have a plus c on the end because we're not evaluating with upper and lower limits of integration like we were in 4.4. But we are going to evaluate it at a specific location, namely when u is equal to x cubed minus 4x. I mean, that's what u is. It's x cubed minus 4x, because we just relabeled it for the moment because it was cleaner, really. So if I go backwards and I resubstitute u back in for what actually it was representing, then I end up with the sine of x cubed minus 4x plus the c. And that's exactly where I began, except for maybe there wasn't a plus c, right? Because we get general antiderivatives and they can shift up and down like we've talked about before. So I wanted to show you where it came from, why it's going to work for us, and what we're looking for when we're making our substitutions. We're looking for the piece that when I take the derivative of it, it's the other piece. So let's take a look at an example where it starts out sort of, well, we aren't working from taking a derivative standpoint. We're actually starting out with an antiderivative question. So if you're taking a look at this, there are two pieces that look like they're multiplied, right? And because there are two pieces that look like they're multiplied, this is an opportunity to take a look and say, is it an antiderivative that can use u substitution? Okay? So we saw some on your gateway where you can actually just distribute and clean it up, right? You can do a little algebra. It works out just fine. There's no algebra to work out here. I've got a cube root function, right? That's no good. I can't just distribute that through the other piece and clean things up nicely. I don't have that as an opportunity. So I do have a potential place where I have an inside function, though, namely what's underneath the radical. Now, the question of whether or not it will work is if everything that I highlighted in red, if I take the derivative of that, do I end up with the other piece that looks like it's being multiplied? And the answer here is, yeah, I do. So what I do is I actually make a substitution. I write over here to the side u equals, and the part that's in red is the part that I'm identifying as my inside function. It's 3 minus 4x squared. And then what I'm doing is I'm going to take the derivative du dx. Okay, so I'm taking the derivative of u. Well, that's negative 8x, right? And then I can adjust and I can move the dx to the other side so that I can find out that du is equal to negative 8x dx. Okay. If you want to simply write this step down and not write this one at all, that's fine. I mean, that's where our goal is to get to anyway, is to write du equals with some stuff by dx. That's fine. But if you need to see that step that I just X'd out, then show it. I'll show it for a few steps, or for a few of our problems that we're working just to make sure everybody's good. Okay, so the whole goal in identifying the u and the du is to rewrite this function with the antiderivative, to rewrite what I have in a simpler way. So if you'll notice, the script s, that didn't go anywhere. The cube root didn't go anywhere. But the part that's in red has a new name. It's called u. And then the part that's circled in blue, along with the dx at the end, also has a new name. Its name is du. So I'm replacing it for the pieces that I've identified as my substitution. And the reason I'm doing it is because it changes the antiderivative into something that's much easier to work with. Appropriately, by the way. You can't just change things to be easier to work with because it's fun. Right? Like, that's not okay. But I mean, like, it appropriately changes it. It makes it easier to work with. So as we're taking a look here, this cube root of u would be u to the 1/3. And then I can take an antiderivative. So what's the antiderivative of u to the 1/3? Right. And I have plus c at the end. All right? I know we haven't had plus c on there because we've been doing evaluation in 4.4, but there are no evaluations on the first few of these anyway, so we put plus c. Okay, so remember, this piece and this piece are like the ending and the beginning of parentheses. They're telling you what to do, that is take an antiderivative, and the du at the end is telling you what the variable is that you're using, and the variable here is u. Yes. Sometimes I have people who tell me that they were reminded that the du goes away when the plus c comes in. So it's another thought that you can kind of keep in the back of your mind. If you've got the plus c, there's no more du, and vice versa. All right, so we're going to clean this up. If the problem started with u, it can end with u, but this problem didn't. It started with x, so it needs to end with x. So the 4/3 as a denominator is the same as 3/4. The 4/3 as an exponent is the same as the cube root. So this is the cube root of u to the 4th. All right, so that's just rewriting with the algebra. And then I need to have the substitution step where the u is evaluated back with what it's actually representing, which is 3 minus 4x. I'm sorry, was that right? 3 minus 4x squared. So I've still got the cube, or the 3/4. I've still got the cube root, and I have 3 minus 4x squared to the 4th plus c. It's perfectly fine with me if you leave it like this, just to let you know one other way that you might see it written, just in case you're checking another resource and you're like, what did they do? How did they get that different answer? Mine doesn't look like that. They might also do this. They might leave the, is it 3/4? 3/4. They might actually have 3 minus 4x squared here in front, and then a 4th root. Was it 4th root? Cube root, sorry. Cube root of 3 minus 4x squared underneath, plus my c. What they've done, if they decide to write it that way, is they've said, hey, look, there's 4 of these underneath here, right? It's like having x to the 4th, or u to the 4th, and they're saying, oh, look, u to the 4th means there's a u to the 3rd. The cube root of u to the 3rd means I could pull it out in front, okay? And then one of them still stays underneath. I don't need you to rewrite it that way. I just want you to recognize if you see it that way, it's not something different. It's really just another version of the same answer. Okay. Any questions about either of those versions of this answer? And you're done at that point. There's nothing else to do. Okay? All right, let's try another one. Now this one doesn't quite look like a product, right? In fact, it doesn't look like a product at all. And if it's going to use u substitution, it needs to look like a product. So is there a way that I can rewrite this that looks more like it's a product rather than a quotient? Yeah, everything that's in the denominator can come up to the numerator with a negative exponent. So that's the first thing we're going to do. And when I say everything, I mean everything. So as in, it's going to actually have, I'm going to put that part first, the 1 plus x to the 4th, all of that to the negative 2nd, right? All of it comes up with the power 2 becoming a negative 2. And then I've got the x cubed dx at the end. Okay, is that all good? Now it really looks like a product. The other thing that does is it helps you to identify that there is, in fact, an inside and an outside of what's going on, right? It does look like something is embedded inside of another function. And so if you take a look at the piece that's in here, this looks like it's inside of something else. It kind of did already in the denominator, but even more so when we pull it up. So if that is my u, and that's a good first step is to think that it should be because it started in the denominator and now it has a power negative 2. So I have 1 plus x to the 4th. What would the derivative, du dx, of 1 plus x to the 4th be? Yeah, 4x cubed. Okay, now, that's not exactly what the other piece of this function looks, or this antiderivative looks like, right? There's no 4 there. Agreed? The x cubed is there, but there's no 4. So we do have to deal with that just a slightly different way. So if you take a look over here, I know that I need to move the dx to the other side anyway, right? So when I move my dx to the other side, I'm going to move my 4 over here as well. So let me show you what that means. So I'm going to look like I'll do it in 2 steps actually, just to make it real clear. So this is du is equal to 4x cubed dx. Okay, so everybody good with that step? And then I'm going to move the 4, so this is going to look like 1/4 du is going to equal x cubed dx. Okay, is that all right? Okay, so So why did I do that? Well, the reason I did it is because the value that I'm wanting to replace is x cubed dx. There's no 4. So if I get the x cubed dx alone, then it mirrors exactly what I wanted it to look like. They are identical. And so the part that I've circled in blue simply is equal to 1/4 du. So when I replace it, it doesn't just get replaced by du, it gets replaced by 1/4 du. Okay? So coming back over here into doing the replacement, the part at the beginning that's in red is now u to the -2. The part that's circled in blue at the end is 1/4. That looks like a 1/9. Let's try that again. 1/4 du. Okay? All the pieces just get replaced. 1/4 is just a constant. It doesn't really affect anything. It's just part of the final answer, right? So I don't have to do anything differently with it. It just needs to be there. So my answer is going to have a 1/4 in it. What's the antiderivative of u to the -2? It's u to the -1 over -1. And then anytime I take an antiderivative without limits of integration, I have plus c. Okay, so there's a couple things that have to happen. This has to be cleaned up. The original function did not have powers that were negative. And I also have to replace u's back with x's and what they're actually equal to, right? The equivalent pieces. So I'm going to do the cleanup of the algebra first, and then I'll do the replacement last. So this is negative, so I've got a -1/4. And the u to the -1 just means u in the denominator. So this is what the algebra simplifies to, -1/4u. And then I replace u with what u is equal to. So I have negative, I have 1/, here's my 4, and then the u is 1 plus x to the 4th plus my c. If you want to multiply the 4 through, you can. It's not going to hurt anything. If you want to multiply the negative through, you can. It doesn't hurt anything. But it's also perfectly acceptable to leave it right there. Let's say you wanted to make sure that you really did it right. You got the right answer. What would you do to make sure that this really worked? I think you're about to say it, Jeffrey.
Take the derivative.
You would take the derivative. If you took this and you took the derivative, it should end up looking like the piece that's inside the integration symbols, right? It should end up giving you x cubed over 1 plus x to the 4th squared. And it will, by the way, it will. So if you're ever wanting to make sure, like, did I do it right, you always have the opportunity that you could actually take the derivative and check. Okay? All right, let's try another one. Oh, this one looks like there's some trig going on, doesn't it? Yes, indeed. All right, do you see something that looks like it's inside of something else? Yeah, sine has something that's not just x. There's more involved in the interior of sine. It's x to the 4th. So this piece right here, I keep using red, so I'll just go with it, is going to be what's inside. And you see that there's another piece over here, and it's kind of written at the beginning, but it's actually looking like it's a product with the piece of sine. So the part that's red, the inside part, is going to be our u, x to the 4th. What is du dx? What's the 4x cubed. The derivative of x to the 4th is 4x cubed. And then if you multiply the dx to either side, you have 4x cubed dx. So this part at the end, that's the dx, and the part at the beginning, that's the 4x cubed, those pieces go together. Okay, just like all the other things that you've done in mathematics since you were very young. Commutativity works, right? So we can switch orders of things if need be. We can identify them. So I have an integration symbol. The sign does not go away. Plus u. X to the 4th is u. And then the blue pieces that are the 4x cubed and the dx are du. Okay, this one feels actually quite a bit like the very first one that I was showing you as an example. What is the antiderivative of sine of u? What is it? Close? Negative. Negative cosine of u. And I need a plus c, right? You need a plus c. Good. And then there's no algebra to simplify in this. There's no trig to simplify either, actually. All I have to do is my substitution step to back substitute, basically, at the end. So I have negative cosine of x to the fourth plus c. This is actually a really good one that if you visually check it pretty quickly, you'll see that if you take the derivative, it would work. So what's the derivative of cosine? Well, it's negative sine, so the negative will cancel at the beginning. The x to the fourth stays the same on the inside, and the derivative of x to the fourth is 4x cubed. So you can see that one very quickly, that it actually works out if you do the substitution, or not substitution, but if you do the derivative, it goes back to where you began. All right. So again, this one does not look like it is a product, right? And whenever there's trig, there's a couple of possibilities. One possibility is that it could be much like this problem here, where I simply move something up and make it a negative power. Like, that's a possibility. And I think that's how this particular one works out. But another possibility, just so that you're aware, is that it could be that you want to do a trig substitution, right? So I put, Jeffrey actually told me that one of my trig substitutions that I mentioned in class was not actually written on my sheet, and I changed it so that it's there. The trig substitutions that we've talked about as being ones that you should know are the Pythagorean identities, the quotient identities, and the reciprocal identities. And those are all actually listed inside of our Canvas classroom on a particular page if you're less comfortable with those than maybe you were when you took trig. So that's another possibility. So we don't really know, looking at this, which one we're going to want to use. So it's a good idea to just try one and see what happens. I do, in fact, have this cosine cubed in the denominator, and if I were to rewrite it in the numerator with a power negative 3, we can see if that will work. Now this is different than the last ones because on this one it's the power that's the exponent, much like this problem over here. Okay, so I didn't say the power that's the exponent, I meant the power that's the outside function, right? Whereas on this one it was the sine that was the outside function, right? Because it was embedded inside. But on this one, the only inside function that I have is actually the cosine function itself, because it's raised to the power of negative 3. And that's actually very friendly because u being cosine of x actually does in fact give us a derivative. That's the other piece that's being multiplied. What is the derivative of cosine of x? Yeah, it's actually the negative one. It's negative sine of x. And then if we move the dx, right, then the du is equal to negative sine of x dx. Now, I don't have a negative in the problem, right? I mean, it's just not there as it is. So, oops, I don't know why that says just d. That should say du. So the negative can be moved to the other side, right? This is negative du then is equal to sine x dx. So when I'm replacing this blue circled piece at the end, I will replace it with a negative du. And I'm replacing the cosine of x in red. I'm replacing it with u. So this is the antiderivative of u to the negative third times negative du. Okay, if it bothers you to see the negative written like that, you can write it as negative 1 du. That's another way of writing it. It's just a constant. It's a negative constant, but it's just a constant. So the negative is just going to be part of the value, or negative 1, right, part of the antiderivative. But what is the antiderivative of u to the negative third? U to the negative second over negative 2. And look, there's that negative is going to cancel, isn't it? So I'm not going to have a negative anymore. Plus c at the end. And then if I rewrite this, the algebra, then I will end up having a 1 on top, the 2 is still on bottom, and u squared's on bottom, plus the c. U is cosine, so when I plug it back in, or when I plug it back in, I have cosine of x squared plus c. You can leave it like that if you'd like. If you want to see it written in a more friendly fashion, you can write it as cosine squared of x like that, plus c. Either of those will work at the end. If it had not worked, right? If it had not worked to do the u substitution that way, then I would go back and I would start looking at, well, what is sine over cosine? What is cosine over sine? What do I have that I could do a quotient or a reciprocal or some of my other identities to make this usable, right? That's what I would do next. So that would be another option here. All right, take a look at what's going on next. This one is actually a slightly different question. It doesn't start out with the integration symbol and the dx at the end. It says to find an equation for the function that has the given derivative and whose graph passes through the given point. We've seen this direction before. We did it back in section 4.1. We just didn't have need of u substitution when we did it. Okay, so what this is actually entailing is that we're going to do the exact same thing that we did on these problems, except we're going to figure out what the c is at the end. And the way we're going to do that is with the additional ordered pair point, pi over 2, 2, that they give us for the particular function we're working with. Okay? So that's the only difference, is that we have this additional step at the end, which is figuring out what is c. So when we start this problem, we're finding an antiderivative, right? So we're going to find the antiderivative of the secant squared of 2x dx. That's what we're going to be finding. But again, the reason that we're seeing this happen again in this section is because we're going to need to use our u substitution in order to do that. So this one's an interesting one, though, because it actually doesn't look like there's a product. In some sense, it's sort of, it is a u substitution, and I want to say that it isn't, but it feels like a kind of silly one, and you'll see why as we work through it. What looks like it's inside of something else here? What's the inside function? Nope. It could be. So you could be identifying it so like this. So you could be identifying it like that. We don't actually like that very much, and here's why, is because we actually know an antiderivative for secant squared. Whose derivative, let me say it that way, whose derivative is secant squared? Tangent. So while that would be a very viable option, depending on what the functions are, it's not necessarily all that helpful on this particular one to do it that way. There's a better choice. The other reason that it's not helpful, Kaylee, on this one is because if I let the u be the secant 2x, du would have another trig function that's not in my problem, and that would be a problem for me too, and I would end up stuck. So good thing to try, just doesn't end up working on this one. So if it's not the whole secant of 2x, what else could the inside function be? It could be the 2x, and that's actually what will work on this particular one, all right? And this is also why I'm saying it's kind of a silly one, because what's the derivative of 2x? Don't overthink this. It's 2. Yeah, it's 2. So the du is just the number 2. It's not a very exciting du. I mean, it's just not. It's just a number. It's not really even got a variable in it, right? So it's not very exciting. Not only that, but did you notice that there's no additional 2 out here with the dx? It's just dx, right? So it feels really funny. So the red part's my inside function. We did it correctly. But over here, what I actually need is I need this 1/2 du to be set equal to the dx. Because dx is the only other piece that I have being multiplied. I don't have any of the values. But anytime I'm dealing with a constant, I can shift it between the two sides of the equation, and it's okay to do that. So when I'm doing my replacement here, the part that's in blue is actually going to be replaced by 1/2 du. I still have the secant squared, and the 2x is u. So this is the function, if you will. I'll put the 1/2 in parentheses since it looks a little funny. But this is the function I have. Okay, the 1/2 just comes along for the ride. I don't have to do anything with it except for bring it along. And then you guys told me just a moment ago that the antiderivative of secant squared was tangent, right? And then I have plus c. Now, this is the function that I was looking for. Almost, right? It's got a u in there. It's not supposed to have a u, because this actually says I'm supposed to be in terms of x. So that's the first thing I need to do. I need to go back and put it in terms of x. So this is 1/2 tangent of 2x plus c. So that's the first thing that I needed to fix or to clean up. The second thing is that the whole point of this particular problem and the way it was worded and so forth is that I can find the c at the end. And I can find it using the initial condition. That's what they usually call this particular point when they give us a point like this, is an initial condition. And I can do that by evaluating, right? So pi over 2 is my x, and 2 is my f of x. So I have 2 on the left, and I have 2 times my pi over 2 as my x, and I can solve for c. If you want, you can multiply the 2 to the other side as the 1/2 as a 2 to the other side. Let's just start right here, though. This is tangent of 2 times pi over 2. So what is 2 times pi over 2? That's pi. What's the tangent of pi? It's actually 0. That doesn't always work that way. But your unit circle can help you to remember those pieces if you need to go back and think about it a little bit. So this is actually 2. This is actually 0 because the tangent of pi is 0. So c is 2. So the end result of everything that we did is that we found out that our function, f of x, is equal to 1/2 tangent of 2x plus 2. All right? I think the directions are the same for the next one. So before we move there, any questions on that one? Okay, I don't think it is actually, now that I'm looking at it. Nope, it's not. I'm sorry. Okay. This one actually looks a lot like these, right? It looks like a product. Agreed? What do you suppose the inside function is here? What should it be?
2 minus x.
Yeah, it should be the 2 minus x, and it is. This one has a little bit of a weird thing that happens, but it should be the part that's underneath the radical. Does everybody agree with that? I mean, that's what's inside of something else. It's inside of a radical. So this is the correct identification. And if I do du dx, what will I get? What's the derivative of 2 minus x? Just -1, right? Just the negative that's associated with the x. This is -1. And if I rewrite this, this is du is equal then to negative dx. And like that's fine, and I can shift the negative if I need to. There's a problem. What's the problem?
It's not.
That is not what is outside in front, is it? It's not. So what do we do about it? Well, there is something that can be done. It's just a little different than what we've done before. It's supposed to be all the pieces that is blue, right? It's supposed to be that stuff. And it simply isn't. So take a look at what we do when this weird thing happens. I have an equation that identifies how u and x are related, right? I do. U is 2 minus x. So what I'm going to do next is I'm going to solve that equation for x. In other words, if u is 2 minus x, what is x? Well, you can move the 2 to the other side, right? So it can be u minus 2. And then that's negative, yeah? And then I can rewrite it so that I distribute the negative through the other side, right? Divide by -1 or multiply by -1. So this is actually 2 minus u, or negative u plus 2. In fact, you know what? Let me leave it written as that, just because I've got that piece that's negative in there. -1. That's what x is. Agreed? Okay. You know what? Never mind. I don't think I want to do that. It's going to make it look weird later. I'm going to take it back. Let's just do 2 minus u. All right, so now what? Well, I need to do all my substitutions. I just have 3 substitutions to do this time. I need to replace the dx. Okay. I need to replace the part that's underneath the radical. Okay. And I need to replace the part that's in front of the radical that's unfortunately not associated with the dx this particular time, at least not in the sense that it can easily substitute it. So what does it look like? Well, let me actually do it with some colors. This is the blue part that I mentioned before, and if you come down here, you'll notice I don't have the negative, so my dx is actually negative du. So the blue part will get replaced by negative du. I'll use colors. The radical part, the square root part, is still the u part, right? All this is still going to be u. Okay, all that's what I did before. The part at the beginning is the part that looks a little bit different now. Now I have an integral, and I need to replace the x with what x is equal to. But x is actually equal to what?
Negative u plus 2.
Negative u plus 2 or 2 minus u. So here at the beginning, I've got, I'll write 2 minus u, and then I have my plus 1. I simply replaced the x. Let's go with purple. I replaced the x with 2 minus u. I agree it still looks weird right now. And in fact, you might look at it and say, how did that help me? I still have just as much going on. And in some sense you do, but what's going on is actually easier to work with. So let's clean up a little bit so you can see that what's going on is easier to work with. So I have 2 minus u and I have plus 1, so this is actually 3 minus u. Is that okay? Got 3 minus u at the beginning. There's a negative, so let me actually write this as u to the 1/2. And then we'll move, well, let me write this as negative 1 du, and then we'll get rid of the negative here in just a sec. So I have commutativity properties, so I can move my negative around, so this can actually be written as u minus 3 by distributing the negative through it. Okay, so is everybody okay so far? All right? So again, why is this better than it was before? The reason it's better is because while there is still one piece of this that has addition and subtraction, the piece that has addition and subtraction is not underneath the radical. Right? What's underneath the radical is simply one variable, nothing else. And the reason that that matters is because it's easier to work with. So take a look at this. I can actually distribute the radical part, the u to the 1/2, through the parentheses. So I can rewrite this as u to the 3/2, because that's what u to the 1 times u to the 1/2 is. It's u to the 1.5, or 3/2. And I can rewrite this as 3u to the 1/2. And I couldn't do that before, because I had addition or subtraction going on underneath the radical. So my goal when I have this is actually to eliminate the addition and subtraction underneath the radical, so that I'm able to do the algebra with this to make it work more easily. So, what's the antiderivative of u to the 3/2?
2/5 u to the 5/2.
Right? So u to the 5/2 divided by 5/2. Dividing by 5/2 is multiplying by 2/5. And then I have minus the 3, and what's the antiderivative of u to the 1/2? Same idea, right? 2/3 u to the 3/2, or u to the 3/2 over 3/2. Plus my c, just like before. What a mess. Okay, so let's clean this up a little bit. There's a lot of things that we could do to clean it up. I'll show you where it's acceptable to stop, and then I'll show you a couple other steps that you might see happen so that you're aware of what else you might look at and then see happening. The 5/2 actually is the same as the square root of u to the 5th. So this is 2/5, and then I have the square root of u to the 5th. And then the 3's here cancel, of course, so this is minus 2. And then I have the square root of u cubed plus c. So that's my algebra step to rewrite. And then I have to do the substitution steps. Those are non-negotiables. You absolutely have to do both of these steps. So this is 2/5 square root. Let's see, u was 2 minus x. So this is 2 minus x to the 5th minus 2. And then I have the square root of 2 minus x to the 3rd plus c. Okay, so this is the absolute first place that you can stop and actually be complete. Okay, I mentioned before when we have these powers underneath the square roots that there's other ways to clean them up where you can pull things out in front and so forth. And this one actually has a very nice way of doing that. So I'd like to show it to you just so that you're aware that this is helpful. And it does end up being even more helpful if you do end up continuing in calculus and have to set things equal to 0 and factor and things like that. So in particular, what did I have my number? 2/5. So this is 2/5. And then I can pull out the 2 minus x squared. And then I have the square root of 2 minus x. And then I have 2 minus 2. And it's 2 minus x, and I have the square root of 2 minus x if I had space. Okay, so that's another thing that can happen. I'm just going to verbalize one other thing that you can do. Because each of these have a square root of 2 minus x in them, you could factor that piece out, right? So you could actually pull that out and recognize that you can actually clean up the 2/5 2 minus x squared and the 2 times 2 minus x and simplify that algebra piece. Okay, so I'm not going to work through that, but that's another thing that could happen. So perfectly fine for you to stop down here at the bottom and not do what I just did. But if you see somebody, you're verifying an answer online or something like that, you might see that happen. All right. The last thing that we're going to take a look at this section, and I may only have time for one of them, and I'll post the solution for the other one just so that you can see it, is what happens when I do use substitution and I actually have limits of integration. Okay? So limits of integration is what we did in the last section where I had numbers on the top and the bottom. How does that change if I'm doing use substitution? And the reality is it doesn't really change a whole lot. You do everything that I've just been doing, get everything back in terms of x, and then you plug the numbers back in. So it's just one more step at the end where I don't have the plus c's because I'm plugging in the numbers. So if we're taking a look at this is kind of a messy one, but I also chose it on purpose because I wanted you to see what happens when it looks like there's multiplication, but the multiplication looks like it's happening in the denominator. Okay? So the part of the denominator that actually looks like it's got an inside function still is this piece, because all of that's raised to the power 2. Does that make sense? Yeah? Okay, so as I'm taking a look at rewriting this, I'm going to leave this part here just like it is, the 1 over square root of x. But the part that's in the denominator that has a power, I'm going to pull it up to the negative of that power. Okay? That's the part that looks like it's got an inside function anyway. So I'm not going to mess with the part that doesn't look like it has an inside. Still have 1 to 9 dx. The u part inside is the 1 plus square root of x. And if you think about what that looks like in exponential form, it's 1 plus x to the 1/2. So when I'm taking the derivative du dx of this, I've got the 1/2 x to the negative 1/2, right? Like that. And if I rewrite this, du is equal to 1 over 2 square root of x. And I move my dx. So do you see that square root of x that's now in the denominator, just like the square root of x that I left in the denominator? Yeah, it's there. So this piece right here, it matches this portion of what I have. So what do you suppose I'm going to do with the 2 that's currently in the denominator? Yeah, I'm going to move it over to the other side. So I'm going to rewrite it with, and it's multiplication now, so this is 2 du is equal to 1 over the square root of x dx, like that. All right, so all the pieces can get replaced. Here's the catch. The 1 and the 9, that applied to the variable x. Agreed? The variable I'm about to put in here is not the variable x, it's the variable u. So when I rewrite this with the variable u, I don't write the 1 and the 9. I'm just going to leave them off for now. They're just not going to get written. So I have 2. I have well, it's all shifted. So I've got a 2, and I've got a du. I'll just put them where I want them to be. And then in between there, the 1 plus the square root of x to the negative 2 would be u to the negative 2, right? Because that's what I identified as u. And I take the antiderivative just like I've been doing on the previous problem. So the 2 stays. The antiderivative of u to the negative 2 is u to the negative 1 over negative 1. And I have been putting plus c's, but I don't need to because eventually I'm going to have numbers that I'm going to put in here. So put it if you want to or don't put it. It really doesn't matter. I have negative 2 here over u. But I know that my u, you don't have to write this part right here the way I'm writing it, but the u is actually 1 plus square root of x, right? So I have negative 2 over 1 plus the square root of x, and I am going to evaluate that from 9 down to 1. And because I'm putting the 9 and the 1 in is the reason I never put the plus c. So I have negative 2 over 1 plus square root of 9 minus negative 2 over 1 plus square root of 1. Okay, so I'm evaluating it just like I did back in the last section. Square root of 9 is 3. So this is negative 2 over 1 plus 3, which is 4. This is minus the negatives. This is plus 2 over 1 plus square root of 1, which is another 2. So this is 2 over 2. So I have negative 1/2 and positive 1, which gives me a positive 1/2. And so here's what I'm going to do. I'm going to pause this video right now. I'm even saying it so that you guys know later. I have one more question that I want to put in here, but I don't want to keep you past the 9:50 time. So I'm just going to run back over to my office. I've got probably 3 more minutes of recording. So if you come back in here later to watch the last example, just fast forward to the very end, watch the last 3 or 4 minutes, and you'll be good to go. All right? All right, our last example, number 8, similar kind of question where we have these limits of integration and we're going to be using u substitution. It's worth noting that this one has addition involved, and so there's 2 pieces of this problem. One of the pieces of the problem is the sine of x1 at the beginning, and that piece right there doesn't actually have any need at all for a u substitution. So we're just going to separate the 2 pieces since one piece could use it and the other piece doesn't need it at all. So we've got cosine 2x at the end here. Now the first piece, we'll actually draw a line kind of down the middle here, and we'll just work the first piece, and then we'll come back to the u substitution in the second piece. So the antiderivative of sine of x, of course, is negative cosine of x. Again, we don't need the plus c because we're actually going to be evaluating at pi and at 0. So I have negative cosine of pi, and then I have minus the negative, so minus negative cosine of 0. Of course, minus negative would be plus, right? So we've got that. The cosine of pi is actually negative 1, so I have the opposite of negative 1. And then I have the cosine of 0, which is also 1, so this is going to be 1 plus 1, or 2. So half of my problem has the answer 2. The other half over here, the cosine of 2x, is going to have a u substitution, right? So just like when we were doing these in class, I have this part is my u, so my u is the 2x. The derivative, the du dx, is actually 2. So du is actually 2 dx. Of course, there's no 2 in my problem, right? So we can move the 2 to the other side as a 1/2. So the dx itself is going to be replaced by the 1/2 du. So we have the integral from, well, the cosine. We're going to leave the limits of integration off just like we talked about on the last one because I'm replacing the x's with u's. So this is the cosine of u. And then the dx at the end is 1/2 du. So the 1/2 can be rewritten, right? It doesn't affect anything. The antiderivative of cosine of u is the sine of u. And we're going to be evaluating that. Oops, I'm sorry, not evaluating just yet. We're going to be replacing that u with the 2x. So I have 1/2 sine of 2x. Now I can evaluate at the pi and the 0. So I have 1/2 sine of 2 pi minus 1/2 sine of 2 times 0, or 0. So the sine of 2 pi, of course, is 0, and the sine of 2 times 0 is 0. So this ends up being 1/2 times 0 minus 1/2 times 0. It's a big whopping 0, right? So 0 on this side. So I have 2 plus 0, so my final answer is actually 2 on this particular problem.